Let's get started. I talked about Roche analysis a couple of months ago, October 25th, and that's a subset of what I'm going to talk about today, item of response theory. And since we only have like 30 minutes or so, I'm just going to show you how to think about it, what it's used for. If we want to talk about how to do it, that's a different level of technical conversation. Happy to do this item analysis with you, or we talk about it because it's a favorite subject. This is a Prezi, which can make you motion sick when you're eating. Anyway, what is IRT and why should we care? What is it for? It's for measuring and for model and hypothesis testing. The measurement aspect of this is the important part. And what are we going to measure? And that's the crucial question, is what do we measure? Okay, I used this example last time. We send these little things to Mars to poke around. How many people can answer the question, was there life on Mars? Do we know? Do we know yet? No. It's science is such that it keeps drilling, so to speak. But let's say that the life that may have been on Mars when water was there is not carbon-based, like ours is. It may have been silica-based or silicone-based or silicon-based or uranium-based or something. So when we're drilling into these rocks, we're looking for evidence of life as it existed on Earth, or as it exists on Earth. So if we're looking for the wrong thing, we're not going to be able to answer our question. That's the point. If we're looking for Earth-like life on Mars, and it never existed like it does on Earth, then we can drill all day, we can send all kinds of things up there. We're looking under the wrong rocks, so to speak. Okay. So in humans, measuring humans in the wild, as one of my colleagues at UA talks about, in health and sickness, we need to measure the right things. And all the analysis in the world, and I'll make this point several times, all the statistics in the world won't straighten out a bad measurement. All right, so this is an idea that's, we're looking inside of a person for their blood values or whatever, or their personality or their intelligence, but we're measuring something called a theta. And a theta is just a general term for the underlying construct we're trying to measure. It's a fancy way of saying that. But theta is intelligence, IQ, if we're going to build a test, preferences, manual dexterity, which is closely related to being a good physician or dentist, pre-cancer or cancer, if we can predict cancer risks or early stages, we're much better off than trying to manage the disease or some other disease susceptibility. So that's what theta is. So when you think about it, when I say it, that's all it means. It's the thing we're trying to measure. So again, the world that I and most of us deal with has this kind of complexity in a way. The data, once we get the data, and sometimes people show up in our offices and say, analyze this, and it's a mess, and there's no way it can be analyzed. How many have experienced getting a mess? And all you have to do is press a button, and the data gets analyzed. You know, that's what the same person that brought the data to you will say. So this is a big deal, but the research machine is more than data analysis. That's my point. And it's a very complex profession. It has a higher and higher levels of complexity and understanding. And you could actually specialize in different aspects of statistics. But we need to balance that with measurement. Again, if we're measuring the wrong thing, we can't fix it in the analysis. So we'll just talk about that here. So we need to decide what we're looking for. In many cases, there are validated tests that we can look up, and we can find just what we need for manual dexterity or IQ or something like that. Medical admissions tests, we think they're highly predictive of eventual success as a physician or success as a student, probably more likely than beyond that. We're not too sure how to test for. So what is it we're looking for? We need to spend a lot of time on this idea of what it is we're trying to measure. And a quick example, this is a work that I did with the pharmacy department down at University of Arizona. And I showed this briefly last time. But we were looking here for ability to predict, it's knowledge actually, of drug-drug interaction. And we were comparing nursing students to medical students to pharmacy students. And so we invented this scale where we could measure their ability to recall what drugs interact. Important to all our health professions that are involved with pharmaceuticals one way or the other. So the easiest is down here, nitroglycerin and Viagra. That's, everyone got that right in all the professions. Why would that be? It's on TV every night, right? And as I like to say, I'm glad my grandmother's dead, because I wouldn't want her to see these commercials, you know. But she would just say, oh, that's awful. But the world has changed. Acetaminophen and codeine, and then the hardest questions of all are at the very top. Simvastatin and itraconazole and warfarin and what Dick said. So over here is a distribution of the people who are taking the test. And you can see it's not clearly equally distributed. I superimposed this normal distribution line on there, but there's quite a few people down here at the bottom that are not very able to recall the drug-drug interactions. So we're looking at two systems here. One is the people, and the other is the item difficulty. And at the top of the difficult items, the most difficult items, in a sense, if people answer those questions correctly, they're probably going to get the other questions below them correct. So in a sense, those top 2, 3, 4 things replace having to test for the more simple drug-drug interactions. Does that make sense? So this is the secret to computer adaptive testing, where if you hit a couple things and you're correct, you can jump over them and go to the more difficult questions. The gaps are areas where the test misses abilities. So I put these shaded figures in here for item gaps. So if someone falls in here in their ability, we're not going to pick it up. We're going to see that they know this, and we might assume that they only know their really low ability, whereas they're somewhere in here, and we can't see it because we don't have an item that fits in that gap. Any comments, questions on that? Kurt? Well, they should be mirror images of each other if they're good tests. So what this is saying is it's a difficult test for the people of this ability, or these people are stupid. That's a joke. I don't want to offend any. I don't want to hear from anyone in 20 years that I said something. Okay, so that's a bad test in a way for our particular population because everything's pushed up to the top. This particular population feels that all these items are difficult. And they're students. So we can, sorry about the example there, but we can plot these, each item like this. We can find out that the easier items on this side are being endorsed, and then so on the more difficult items or less endorsed items are to the right. Let me give you a better example. That's not very good. So here's one item, okay, or one test for cancer, one biomarker. And if we look at this one item, we see that the lower endorsed area, where they answer very much, is well represented because the curve goes up to the top for the red curve. Is this your lunch? Okay. And then quite a bit and a little and not at all. So what this tells us is that this item was good. It represents the full range of the theta that we're trying to measure. Somehow. So here's visual acuity or visual ability, and this is a visual. These are visual test items. You can see that this is much more balanced, as per Kurt's question, that the people who are being tested are very, very well measured by the items that we're using to test them with. And here's another ideal item. The theta is across the bottom. These are standard deviation units on the bottom. And so the easy area is well measured on a single item, and so is the most difficult. And there's a nice symmetry in between where we're picking up the abilities here, 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 and here. So it's well covered. There aren't any gaps. And here's some nasty items. This is real life. This is from data that I've taken. This is the way the world looks. So here's a very, I don't know what that is. It's just kind of a mess. And there's nothing that really picks up the lower end of the theta, but everything's kind of pushed up to the top. Not a good item. And then most of these items, if you look at number 1 up there, there's we're picking up, with just 2 responses to that item, we're picking up all the information we can. And the additional responses, like agree and strongly disagree, which it might be in this item, are buried. We're not coming out. So the item is interesting because it's very sensitive to the person's responses, but we're getting what we might call a floor effect. So we're only picking up the lower end and not the higher end. I guess that's a ceiling effect, sorry. So you can see these are all bad items because they don't have a nice coverage across the theta. Does that make sense? Questions? Comments? Okay. So in summary, we want to test that with items that are informative as to a person's ability, or we want to measure with informative components like biomarkers. And one of the ways to think about physical examination, orthopedic neurological tests, is that we might only need a few to get to the point of referring somebody out for more testing. The item should cover the entire range of theta, remove measurement gaps for a scale that detects all levels, which I showed you earlier. And we want stable measures. We don't want them to vary for a certain person over time in most cases. Sometimes we want to find out a mood, but most of the time when we're looking at health and disease, we want to have a stable measurement that doesn't shift around. So, and I said IRT is the basis for computer adaptive testing, and when more difficult items represent information expressed by easier items, we can improve the efficiency of medical and diagnostic tests. So this is a paper that I just published, just got published. More accurate oral cancer screening with fewer salivary biomarkers. I started this in Malaysia. I worked there for 3 years. And we were interested in biomarkers that will tell us if a person has oral cancer without having to go through thousands of tests. You know, biomarker assays can be very complicated. But biomarkers that can be easily preserved in the jungle and shipped out, that won't degrade with the heat and humidity, which is over there. And yeah, I think that's all I want to say about that. So these are the prevalences of disease. And if we look at even a very small prevalence, and these are percentages, 0.0002%, it'll take up to 10, this is the mean, up to 10 biomarkers to be confident that the person has a disease and should be referred out for surgery or more testing. Up at the top, with the prevalence of 2%, we can get away with as few as 5 biomarkers, maybe 4. And this flip side over here is kind of a complex graph, but the flip side here, we're using the least informative biomarkers to start with. So information value of the biomarkers can be ranked such that the most informative ones first, and then step down in terms of their information value. You can get away with about half the biomarkers or medical tests that you would need if you just kind of do a scattershot approach and do a lot of biomarkers and then count the ones that are positive. So I thought it was surprising to me that you can rank order these biomarkers and have them give you better information. And then here's these are the area under the curve plots for each one of the biomarkers that were tested. And as you can see down here, with the specificity and sensitivity of 0.75, the area under the curve, in other words, the correct prediction, ability to predict, is 0.8. If I trim out the biomarkers so it's only greater than these two values, so I can get away with fewer biomarkers to give me the same information. So, any comments or questions? Yes? I used likelihood ratios, which are the sensitivity over 1 minus specificity, and that I found is pretty much a good. I was trying to stay in the distribution-free world of likelihoods. I didn't use logistic regression models. But this represented 137 studies with 12,212 people with oral cancer, oral squamous cell carcinoma, and 25,000 healthy patients. But, yeah. Okay. Dick? Yeah, I think so. Yeah. The positive predictive value, in some cases, where the specificity was 100% or reported as such, the method is not in here, but I couldn't use that because that would divide by 0 on the likelihood ratio. So I would adjust it to a very high level, and there are 2 ways to combine these 137 studies so that matrix, the confusion matrix, you know what I mean? If you add those into the cells, then you kind of get a more realistic sensitivity and specificity of because some studies would just show 100% specificity and 100% sensitivity. That's not realistic. So, Yeah. This is a lifetime of, I mean, this could be a lifetime of work. I could see that, and it could improve medical testing efficiencies, which are not very well explored. I used the biomarkers sensitivity and specificity and area under the curve to come up with likelihood ratios individually between mark. But I didn't put it up here, but the biomarkers were often tested individually, and sometimes they were tested as a panel. So in order to see the contribution of the individual biomarker to a panel, I would compare the panel with the biomarker to a panel without and to the individual biomarker. So I'm trying to, through a regression model, basically trying to find out how much of prediction accuracy was added by having that biomarker. But again, for the most part, I used likelihood ratios to add and subtract the amount of information that was added by that biomarker, which is Steve Goodman did that. Yes. Yes, yeah. I kind of used AUC as an after-the-fact verification, but the likelihood ratio was the primary indicator of information value. Yeah, I'd like to discuss this some more. Since prevalence is so important, I took the prevalence that was of the disease that was listed in each study, and tried to find and found a likelihood ratio that would then could be used for other prevalences. In most, and check this out, in most studies where we're comparing 500 people with the disease and 500 people without the disease, and we look at sensitivity and specificity, we are skewing the data already because the prevalence is 50%. So I hadn't seen anywhere else where they backed that out and said, yeah, that's okay. Yeah, 50% we're getting sensitivity and specificities of this, but what if the prevalence is 0.2%? So it seemed to me it had to be adjusted for prevalence, and that's what needs more discussion, I think. Any other comments, questions? The way it was done in the review, then this is 2014. I think maybe they've come along farther on this. That there wasn't any real consideration of which variables contributed the most to the diagnosis of the disease. I didn't see that. I just saw kind of an array where they pick all these indicators. That is to say, the biomarkers in the saliva were elevated during the disease state among the diseased people. So they must be good biomarkers. And so you could check those out in future research, but if you really want to take a hard look at them, you would look at the likelihood ratio, it seems to me. There were sometimes statistically significant levels of the biomarker between the diseased and the healthy group. I don't think that's sufficient for choosing. So I don't know if the techniques that you're talking about are multiple regression techniques for logistic being the diagnosis, yes or no, or what? Yes? AIC or AUC? Oh, Keki's information criterion. No, I didn't, and I think there's a number of ways to explore this further. Yeah. Well, I think it'd be good to check that out. Yeah. For the most part, I would say that this is a signal detection approach. You would ask that question. Yeah, this was a signal detection approach. The IRT approach would be to, and let's just discuss this for a second, would be to rank order basically the biomarkers that are most predictive of a population with various stages of oral cancer. So you'd have at the bottom, let's see, the people with no cancer, healthy, and at the top you'd have full-blown oral squamous cell carcinoma. The problem is that with the samples that I was just talking about, where you have 500 of each, it's a logistic kind of situation, or bimodal for the population. And so what I was proposing the next step of this to be is to, well, it'd be great if we had people in various stages of cancer or pre-cancer, and we could plot that as the population. But without that, we can simulate each one of the biomarkers as test items and have them at various degrees of accuracy. So they're true positives plus their true negatives over the total for each one of the biomarkers with 10,000 subjects or something. And then ultimately, yeah, and that's another next step, I think, because some of these are delivered in panels and they might be interacting with other biomarkers in a more informative way. I just kind of did the bare bones as to develop this method. So, anyone want to collaborate on the next? Thank you. Yeah, it was a challenge with the complexity, but I thought also that maybe introducing a simpler approach might lead to another way of looking at biomarkers rather than we got 500 with, 500 without, p less than 0.05. Okay, let's try another one. So it sounds like you've done some work in the area. All right. Thank you, everyone, for coming out here.